and I hope you had a nice samba night yesterday night. If you missed it, we should have tonight a barbecue with the students of IMPA. They are organizing this. It's going to happen about 7 o'clock or soft hours, like 7:30. It's going to be in this club that's just around, behind IMPA, and you'll see large crowds moving in that direction at certain points, so you shouldn't have much of a trouble to find it. For those who like precise instructions, it's called Clube dos 17. And okay, then we are going to start, and I'm going to ask Professor Rita de Almeida to introduce our speaker today.
So, good morning to everybody. So I'm going to introduce Christoph Hauert. He is now working at the University of British Columbia. He's doing a postdoc there. He made his PhD with he made his PhD at Kiel in Germany. He's from Switzerland. And his main interests are game theory and evolution populations. And by September, he'll be joining Martin Novak and Francisca. So,
Thank you. Okay. So, first, thanks for this nice opportunity to present my work here on cooperation in social dilemmas. My talk is going to be in two parts. First, I would like to talk about cooperation and social dilemmas in a more general sense and introduce two approaches to address these problems in game theory. And then I would like to turn to spatially structured systems and discuss what happens if we have these special population structures. So to begin, let me start with a kind of a definition of a social dilemma. In a social dilemma, we have cooperators that sustain or maintain or produce some kind of a public good, and we have the defectors that attempt to exploit this resource, and they try to avoid the costs. So we have the situation that a group of cooperators is better off than a group of defectors. And as a third point, we say that defectors must outperform cooperators in every composition. So this leads to a sorry. No. So here we are. Now this leads to a common conflict of interest between the individual and the community. And to illustrate this situation, I've listed here a few examples, because this kind of social dilemmas, they're simply abundant in human and animal societies. And to give you an idea of the kind of problem we're talking about, I just want to address the case of group defense. In that situation, smaller individuals can get together and like this they manage to defend themselves against larger predators or larger competitors. But then from the individual's point of view, it is always favorable to be in the second line. But then if everybody tries to be in the second line, the whole group defense will break down and eventually everybody is worse off. So these were all examples that refer to our sort of present day experiences, but cooperation and social dilemmas, they have played a very important role during the evolution of life itself. And so I mention also just a few of these major transitions that are related to questions of cooperation. For example, when molecules got together to form protocells or genes to form chromosomes, cells to organisms, and finally, individuals to form societies. Now, one of the pioneers to study this very last transition was even earlier than Darwin. It was Jean-Jacques Rousseau in his discourse on the inequality of man. And here I've just shown you the front page of the first edition. But now, with this kind of introduction, overview, let me rephrase all this in a game theoretical way. Now, the first thing that comes to mind when thinking about game theory and cooperation is certainly the prisoner's dilemma. It has become a paradigm to discuss cooperation, and probably its fame goes back to these tournaments that Axelrod organized, and Martin mentioned them already yesterday. So let me start with a brief definition of the prisoner's dilemma. In the prisoner's dilemma, you have two players that simultaneously must decide whether they're going to help a co-player or whether they refuse to help. If they help, this provides a benefit B to the recipient, but helping also involves some cost C to the donor. This means that if both players decide to help, they receive a net benefit of B minus C. But if no one helps the other one, then they just end up with a payoff of 0. Now, if only one player cooperates and the other one defects, then the defector gets the highest payoff of B, while the cooperator is just left with the costs, so he gets minus C. Now, if we demand that the benefits are larger than the costs, then we get the characteristic payoff ranking for the prisoner's dilemma, which is T is larger than R is larger than P is larger than S. Now, to get a better idea of this game, we can write down the a payoff matrix, where you have a row player that competes against the column player. And for simplicity, I rescaled the payoff such that mutual cooperation pays just 1 point. And if we introduce a variable R which denotes the cost to net benefit ratio, then the payoff matrix becomes a particularly simple structure. So if we start off in the situation where both players cooperate, then the row player will face the temptation to defect because 1 plus R is bigger than 1. And if this happens, then the other player will get the payoff of minus R, and so the other player will switch to defection as well, which means that the outcome of mutual defection is a rational choice, and it is a Nash equilibrium, which means that no player can improve its payoff by his own action. Nevertheless, mutual cooperation would be the preferred outcome for the two players, and hence the dilemma. Now, in evolutionary game theory, we look at large populations, and we say that strategies replicate according to their relative payoff, which means their payoff in comparison to the payoff of the population, which is denoted by P bar. So, for example, if the cooperators get a payoff PC, and if this payoff happens to be larger than the average population payoff, then they will spread according to this rate. Now, in the case of just two strategies, of just cooperators and defectors, the replicator equation becomes a bit easier and can be written in that form here. Now, to have everything as simple as possible, we just stick to these two strategies, cooperation and defection, and assume that there are only one-shot interactions, so the players do not adopt any kind of sophisticated strategies, and they don't have any memory or whatever. So, in the scenario of evolutionary game theory, we find basically the same thing as in the classical view, namely that defection dominates cooperation, because the payoff of defectors is always bigger than that of cooperators. And this means that cooperators go extinct. And then it follows that the population as a whole is worse off than if everybody had cooperated in the end. And we again find a conflict of interest between the individuals and the community performance. To give you a few examples where this might occur, this situation might occur in nature, we have that vampires share blood with hungry fellows. We have alarm calls, for example, in meerkat that warn feeding animals from predators. And we have monkeys that groom each other. And finally, fish that inspect predators, preferably in pairs. Now, the problem with all these scenarios is that it's extremely difficult and challenging to find out whether these are true prisoner's dilemma interactions. Because in experimental setups, it is almost impossible to make quantitative measurements which assign payoff values or which determine the payoff matrix. And even the ranking of the payoffs is a difficult issue. There is only a single nice exception to this, and this refers to the interaction of RNA fakes. And that's, as far as I know, the only organism where all the payoff values were determined experimentally. Now, I will come back to these RNA fakes and to the fish later on. But in general, this kind of lack of evidence for experimental support for the prisoner's dilemma has led to a sort of a discomfort with the prisoner's dilemma as the sole paradigm to explain and discuss cooperation. So I would like to return to the definition of the social dilemma and relax it to some extent, and then to see what happens from that. So we keep the first two conditions, that cooperators sustain the public good, and that groups of cooperators are better off than groups of defectors. But we no longer demand that defectors are always better off than cooperators. However, it follows from the second condition, since groups of cooperators are better off than groups of defectors, that groups of cooperators will still be prone to exploitation by defectors. So in this setting, the conflict of interest is relaxed, and it is just a potential. There's just a potential for a conflict. Now, in game theoretical terms, this leads us to the Snowdrift Game. And to give you an idea what the Snowdrift Game is, there's a nice little story. Although it may seem a bit weird to talk about snowdrifts in Rio, but just imagine two drivers on their way home, caught in a blizzard and trapped on either side of a snowdrift. Now the two drivers, they have the option to either get out and start digging a passage through the snowdrift or stay in the cozy warmth of the car. Now the question is, what would you do, or what should you do? Now, before I answer this question, let me rephrase the Snowdrift Game in a more formal mathematical way. So we have two players that simultaneously decide whether they are going to share the costs in order to access a certain benefit. Now, in that case, the effective incurring costs, they depend on the behavior of the co-player. So if both players cooperate, get out of the car and start digging, they both get the reward and they share the costs. So it's B minus C half. But if both stay in the car and wait for a rescue team or spring, then they just get nothing. However, if one player starts digging and the other stays in the car, then the lazy bum gets the whole benefit, whereas the diligent one has to do all the work and gets B minus C. So if we again have that the benefit is larger than the costs, which obviously makes sense, otherwise this would be a boring situation, then this defines the Snowdrift Game with the characteristic payoff ranking given here. Now, I just like as a side note to mention that if we increase the costs, then we recover the prisoner's dilemma. So if the costs increase the benefit but aren't too big, then we get the payoff ranking of the prisoner's dilemma as before. And if we compare these two payoff rankings, then we see that the only difference is that S and P, they switch places. Now this has quite considerable effects on the outcome of the system or of this model. We can again rescale the payoff values such that cooperators get a payoff of 1. And we have again the R that defines the cost to net benefit ratio, which is slightly different because of this 2 than the definition of the R for the prisoner's dilemma. So now we have the situation that if both cooperate, then one of them faces the temptation to defect as before, because 1 plus R is larger than 1. But the other one that gets 1 minus R doesn't face the same situation as before. He won't switch to defection as well, because 1 minus R is still better than 0. So this means that the best decision to take actually depends on the co-player's move. So if you're trapped in this snowdrift situation and you know that the other player is going to dig, then you should stay in the car. But if you know that he doesn't get out, if he's a lazy bum, then you're still better off if you get out yourself and face the cold fact. So in this game we have 2 Nash equilibria, which are CD and DC. And in addition, if we allow for mixed strategies where cooperation is only played with a certain probability, then we find a stable mixed strategy, which is given by the probability to cooperate of 1 minus R. If we look at this game in evolutionary game theory, again, by solving the replicator equation, we find that there exists a non-trivial equilibrium where the payoff of defectors equals the payoff of cooperators. And it's no coincidence that this equilibrium is just the same as the mixed strategy. So here we find that cooperators and defectors can exist, and this equilibrium is stable. But nevertheless, in this equilibrium, the population is still worse off than if everybody would have cooperated. So in that sense, this conflict of interest between the individual and the community persists. Now if we look at examples of the Snowdrift game, so this is very new, and actually a lot of work is here in progress together with Franziska and with Martin. But I just would like to outline the basic characteristics. So if you look at yeast cells, then if they forage, they secrete some kind of enzymes which lies their environment. But this provision of food can be exploited by everybody, even those cells that do not produce the enzymes. So this is would be some kind of a public good that can be exploited. But on the other hand, if no one produces the enzyme, then all the cells are going to starve. So the individual cell is, in that case, is better off to produce the enzymes in order to get access to this food resource. So this situation has exactly the structure of a Snowdrift game. And similarly, there seems to be Snowdrift games in tumor, in cancer. And one of these situations is that the cancer cells, they need to get some kind of a camouflage by sending out a signal which protects them from attacks from the immune system. And again, this producing the signal is a kind of a public good that can be exploited. But if no one produces this signal, then the cancer cells might get destroyed by the immune system. And similarly, it is that cancer cells, they have quite a high demand in energy in order to maintain their higher division rates, and so they need to attract blood vessels. And there it's a very similar situation, that producing the signal to attract blood vessels is again a sort of a public good which can be exploited, but at the same time, if no one produces this signal, and then the sufficient energy supply is no longer guaranteed. And as a third system, I again mentioned the RNA fakes. In just a minute, I will say a bit more about them. And as a last point, I mentioned that the hawk-dove game and the chicken game that were mainly used to discuss interspecies conflicts or competition. These games are equivalent to the Snowdrift game. Maybe I should add that they're at least equivalent under the replicator equation. For certain other dynamics, they're not exactly equivalent. So let me turn to two famous experiments. One thing refers to the predator inspection in sticklebacks. This is one of the kind of standard examples to motivate the prisoner's dilemma. However, the elaborate experiments by Milinski and his co-workers, they confirm only that T is larger than R and is larger than S. And for that, they literally needed to feed hundreds and hundreds of sticklebacks to hungry pike. But nevertheless, P remains unresolved. So there is quite good evidence that P must be smaller than R. But it remains unclear whether P is larger than S or P is smaller than S. And that would just determine whether we have really a prisoner's dilemma or whether it is actually a Snowdrift game. Yep.
Can you just a few words to explain how the game works?
The experiment?
Yeah.
Yep. So in the experiment, they have these compartments here. Here, the sticklebacks start off, and as long as the sticklebacks are in here, they are invisible to the pike that's over here. And what they basically did, they had this wire, and they took two dead sticklebacks, and they put them on the wire, and then they had the sticklebacks in different positions. So in one situation, they had both sticklebacks were in the same. Yeah.
You are going to the technical details, but first maybe you should explain what predator inspection is about.
Okay.
Because it's a very strange behavior.
Okay, thank you. So, yeah, the sticklebacks show this funny behavior that they live in groups of maybe 10 to 15 individuals, and their main predator is the pike. And so whenever a pike is in the neighborhood, then one observes quite frequently that two or more individuals, but usually two individuals of the group of sticklebacks go away from their group, and they approach the predator very closely. And it is not exactly understood why they do that. The most likely cause is that they want to get some information about the state of hunger of the pike. And so it's a very risky enterprise for the two small sticklebacks to approach the predator. And if it is the case that they want to have information about the state of hunger, then it would be, for one stickleback, it would be better to lag behind just a little bit, because like that he would greatly reduce the risk of being eaten, but at the same time he would get probably almost the same amount of information. And what you see is that the sticklebacks, they move forward, and they're almost all the time at level. And so what they did in this experiment, they just wanted to find out the costs of this predator inspection behavior. So in one situation they had the two sticklebacks moving towards the pike, the two dead sticklebacks. And there were at level, and then they did it with different kinds of lags. And by analyzing the experimental data, they found that this relation must hold. But the problem is that the outcome P refers to the situation where no one does inspection behavior, and it would be very difficult to assign a value to this behavior as well.
Thank you.
Okay. So, and the second example refers to RNA fakes. In RNA fakes, Turner and Zhao have demonstrated in very nice experiments in '99 that you can have two strains of RNA fakes in a cell, and one strain is slightly shorter, and for that matter it can reproduce a little bit faster. But in order to reproduce, they need some products that are only produced by the strain that has the entire or the whole length. And with these experiments, they've shown that the RNA fakes are actually trapped in a prisoner's dilemma. But in that case, cooperation could not persist, but cooperators would go extinct. Now, in more recent experiments, they sort of revisited these results, and they had two strains. One were evolved to become defectors, and the other strain was evolved under purely clonal conditions to become cooperators. And if they now let those two strains compete, they found that the success of the defectors depends on their frequency. So here the straight line, that's the performance of cooperators. That's sort of the unit of measure they use. Now for low frequency of defectors, they found that the performance of defectors is considerably higher than that of cooperators. But on the other hand, if defectors were abundant, then their performance was below that of cooperators. So this suggests that in the long run you would get a coexistence of the cooperators and defectors near this value. So this kind of closes my more general discussion of the prisoner's dilemma and the Snowdrift game. And now I'd like to come to the second part and discuss what happens if the players are arranged on a lattice. On such a lattice, for example, the red player here interacts only with its four nearest neighbors. And it also competes only with the four nearest neighbors. So whenever the red guy wants to reproduce, he has to compete with these players. And the reproductive success, we assume that it depends, again, on the relative performance of the individuals, which means on the payoff differences. In that sense, this defines a spatial analog of the replicator dynamics. Now, this scenario lends itself ideally for Monte Carlo simulations, but at the same time, it would be nice to have a little bit a more rigorous approach. So, some time ago, the pair approximation of condensed matter physics was applied to game theory, and we apply this here as well. I just give you a brief outline. In the replicator dynamics, which is a kind of a mean field approximation, the dynamics only depends on the frequencies of the strategies. Now, in the pair approximation, instead of looking only at the strategy frequencies, we look at the frequencies of strategy pairs. So we look at the time evolution of a strategy pair, say S prime, where S prime are the two strategies we have here. So for compatibility with mean field approximations, we must have that the sum over all pairs of one particular strategy must add up to its frequency. And from that follows that the pair frequencies, they must be symmetrical. Now here, that's the important part. That's where the approximation actually comes in. So in the pair approximation, what we do is we approximate the configuration probability of larger clusters by adding or by putting them together from these pair configuration probabilities. For example, if we have a triplet configuration, say S, S prime, S double prime, then we say that the probability to find this triplet is the probability to find the pair S, S prime and to find the pair S prime, S double prime. But in this product, the probability of finding S prime enters twice. That's why we have to divide by the frequency of S prime. Now, just to remind you, in the mean field approximation, the triplet probability would have been just the product of the frequencies of the three strategies.
Sorry. Is this a kind of anonymization approach?
Oops. I wouldn't know. I'm at loss here.
I don't think yet. I mean, the randomization would come when you take limits and you divide by the appropriate thing. So far there is nothing about randomization. As far as I could see.
Mm-hmm.
Yeah.
But I don't know.
No, I wouldn't know. Sorry. So now we are interested in the time evolution of these pair configuration probabilities. And for that, we need to know, or we focus on one individual A and choose a random neighbor B. And then, depending on their neighborhood, they have a certain payoff, say PA, and a payoff PB. Now, depending on that difference, the strategy A will switch and adopt strategy B. And for simplicity, we assume that this is just a linear probability, and the probability is given by the difference between PA and PB, and we say that in the case that that A is better off, then it won't switch. That's indicated by the small plus here. And alpha is just a normalization constant. Now we can put together our the previous approach I showed you to determine the cluster configuration probability plus this transition given by the payoffs. So if A switches to B, then the frequency of the pairs AB decreases. And it decreases at a rate which is proportional to the transition probability plus the configuration of one such part of the lattice. And similarly, the pairs of the strategies of type BB, they will increase. And then we have to do that also for changes due to these neighbors there. And the configuration probability of this whole cluster is just given by this product of the pair configuration probabilities, and we have to divide by the appropriate factors to account for double counting. So we're equipped with this more rigorous approach. We can compare results from well-mixed situations and results from the pair approximation together with simulation results. So in the prisoner's dilemma, we have seen that cooperators go extinct, which is indicated by the dotted line. That is, at least in well-mixed populations or according to the replicator dynamics. But on the lattice structure, substantial fractions of cooperators can persist, at least for low values of R. That's indicated by the squares. And we see that the trend that space is favorable for cooperation is correctly predicted by the pair approximation. Only pair approximation greatly overestimates the region where cooperators can persist. And the reason for that is near this threshold here, cooperators can persist by forming compact clusters. And these clusters, they involve many kinds of small loops. And exactly these small loops are not taken into account by the pair approximation. That's the reason for this big difference. But at least the trends are correctly predicted. And we find that on a whole, if anything, then spatial structure is beneficial for cooperation.
You plot the frequency of cooperators as a time average after a certain number of rounds.
Yes.
And this stochastic updating, so with probability 1, the cooperators will go out as time goes to infinity.
Say that again.
So it's a finite population size.
Right.
And stochastic updating.
Yeah.
So they're absorbing states, right? The absorbing state is either everything is all cooperate or everything is all defective.
Yes, but the system size is large enough that this won't happen.
That's right. So there's a kind of quasi steady state that
Yeah.
you investigate.
Yeah.
And that is independent of initial conditions, but
Right.
largely independent of initial conditions. You know there's only one steady state.
There is it depends on the update rule. That's for one thing. But if you have a stochastic update rule, then it's independent of the initial configuration. There's enough noise in the system.
Chris, are the migration rules in these dynamics, or how do individuals get from spot to spot? Or there's always one individual at a spot, and that individual's behavior evolves?
The individuals, they just stay in one spot. And they reproduce by populating neighboring sites or by imitating the strategy of a neighboring site. But they're fixed in their locations.
But they get killed if another individual puts its offspring there.
Because the overall conclusion is obviously the same that David Sloan Wilson arrived at 30 years ago as models of trait group selection, where he had clusters of individuals that were formed by binomial sampling from a larger population. And it showed that in those circumstances, with that binomial variance in trait group composition, that selected systematically for the evolution of cooperation.
Mm-hmm. Yeah, there are many different approaches to show that some kind of viscosity in a population can favor the evolution of cooperation.
But in David Sloan Wilson's work, each cooperator benefits itself. And I think if you remove that, you wouldn't get cooperation. There's a very subtlety there. He always assumes that each cooperator has himself. But if that wouldn't be there, I think there wouldn't be cooperation in that kind of binomial sample.
That's an interesting point. I have to look at that again, because that would bring us again to the Snowdrift game.
Kind of Snowdrift.
Yeah. Okay. Yeah.
Would diffusion by itself, just like adding a Laplacian, be enough together with the local sort of replicate equation help cooperation, or what that wouldn't be enough?
It wouldn't be enough. There is it's a game. There's two strategies, and if one of the strategies dominates the other one, then diffusion would lead to the dominating strategy. But if this is a bistable situation, then diffusion will lead in the long run to the establishment of the risk dominant strategy. But which can be, if one has, for instance, a repeated business dilemma game, which could be different. But in this simple situation where one has a one-shot business dilemma, then diffusion will not lead to the evolution of cooperation.
Mm-hmm. Okay, I'd like to illustrate this a bit more. So, if we, as I mentioned, near the extinction threshold of cooperators, we have small clusters that form. And in a sense, one could loosely say that they try to minimize their surface. And that just means they try to avoid interactions with defectors. And now these small clusters, they move around the lattice in a diffusion-like fashion. And their behavior resembles a branching and annihilating random walk. And for that reason, for the physicists among the audience, the extinction of the cooperators actually belongs to the class of phase transitions related to directed percolation.
What boundary conditions do you put on this lattice?
Periodic boundary. It's a torus. Now, how quickly the system relaxes into this equilibrium state, I can show you with some simulations. No, that's slow.
What's that?
I'm just waiting for the simulations to come up. Okay. So, okay, that's a random initial configuration. 80% cooperators, 20% defectors. What's wrong here? I don't know. Right. Finally. So you see that quite quickly these small clusters form, and they will decrease in numbers over the time, but that takes quite a bit more time. For now, I just wanted to show you a different thing, and that refers to the average payoffs in this population. So here you see that the average payoff of cooperators, the blue line, is significantly above the average payoff of defectors. But at the same time, the average population payoff, the black line here, is significantly below the blue line up there, which would indicate that the entire, or this one indicates average levels of average payoff levels if everybody cooperates. So we can see again what the strategies on the grid are doing. Looks fairly similar as before. So that would be the equilibrium state, more or less.
If you plot the average number of clusters as a function of time, you said it goes down. Will it reach a steady state?
It should reach a steady state. If you're very close to the boundary, then it occasionally happens that the cooperators go extinct. But here we're reasonably far away, so I expect it to level off. Now, how do the results look for the Snowdrift game? Here we've seen that in the replicated dynamics, cooperators and defectors coexist. I'm not sure whether you can see the dotted line. The level of the cooperators in well-mixed populations is just a diagonal right here. Now, in the spatially structured simulations, it turns out that the populations, that the amount of cooperators generally lie below this line, which means that spatial structure is actually deleterious to cooperation. And again, we have that the pair approximation indicated by the black line predicts the change or the trend in the right way. We have the situation that near the extinction thresholds of either defectors or cooperators, the pair approximation is far less a good approximation, and that's again because of neglecting loops that occur on the lattice. But in the middle, it's a surprisingly good approximation, actually. So the main conclusion is that the spatial structure is not only beneficial, it kind of depends on the game. If we look at a particular snapshot, again near the extinction threshold of cooperators, we find that the cooperators are spread out over the entire grid, and they form a completely different kind of clusters. They resemble more like dendritic structures. And in a sense, again, in a loose sense, one could say that the cooperators try to maximize their surface. And the reason for that is that in the Snowdrift game, it's better to adopt a strategy that's different from the opponent's strategies. And as for critical phase transitions, there seems to be one, but we haven't had the time yet to have a closer look on that. Oops, sorry. I wanted to show you again, maybe a bit faster, how this evolves. So if we again start from a random initial configuration, even faster than in the prisoner's dilemma, the population relaxes into an equilibrium state. And looking at the average payoffs, we find the same picture. So the average payoff of cooperators is significantly higher than that of defectors, but the average population payoff is quite a bit below the payoff for mutual cooperation. So as a last point, I'd like to mention the microscopic patterns that are relevant in the Snowdrift game. So in contrast to the prisoner's dilemma, we have the situation that a single cooperator can survive in a sea of defectors. And this single cooperator can form lines of cooperators. And then in the next step, it can form crosses. But the defectors here in the corners, they're stable. And so they prevent the formation of more compact clusters as in the prisoner's dilemma. And if these dendrites grow further along, eventually the tip of a dendrite may break off and produce the seed for a new such kind of a process. And this eventually leads to the spreading of these dendritic structures over the entire lattice. So that brings me to my conclusions. First, I think the Snowdrift game has attracted little attention in order to discuss cooperation. But I think it's a biologically very interesting alternative, and I hope I have been able to kind of make this point. And I think it could resolve certain reservations or concerns with the prisoner's dilemma as the sole paradigm to discuss cooperation. And secondly, I wanted to show you that although it is generally believed that cooperation favors, that spatial structure favors cooperation, this cannot be made as a universal statement because it depends on the details of the interaction, as we have seen in the Snowdrift game. And to wrap up, I should acknowledge the help of Michael Döberli of UBC and Yuri Sabo from Budapest. For those that would like to learn more or would like to play around with these applets themselves, I'd like to point out this webpage. It's at the University of Vienna, where I was, these virtual labs, they go back to my work with Carl Sigmund in Vienna. And as a very last thing, I'd like to show you some nice pictures. If you have a symmetrical initial configuration and a deterministic update rule, then you would get nicely evolving Persian carpets, evolutionary kaleidoscopes, or whatever. So, and you can again see that they're quite different, whether it's a prisoner's dilemma interaction or a Snowdrift game. Thank you. Yes?
The microscopic scheme you showed how the dendritic structures occurred because of this, what happens in these corners. If you have another geometry, for instance, other neighborhoods, or hexagonal structure, or things like this, how do these microscopic obstructions look like?
They look amazingly similar. So it's the basic properties that you have extensions just in a linear way and maybe along a cross. That's the same. Of course, you have different kinds of boundary conditions, but actually I can show you if you. Just need to. This does not work in a way I was hoping.
Could you repeat the question since I couldn't quite hear the question?
Carl was asking whether these kind of mechanisms to form the dendritic structures, whether they depend on the underlying geometry of the lattice. And it's a surprisingly robust result. And since I can change the geometry, I should be able to get this on a honeycomb lattice. Now the extinction threshold is different for the hexagonal and for the rectangular lattice, but we seem to be close enough to the extinction threshold that you can see that it's again these fragile structures that evolve. Okay. Yes.
I'm having the point of view of really 20-year-old student. I don't look like one, but I try to behave like one. So, just as a novice in the field, I'd like to hear an opinion. What would be the possibility of blending the special route for cooperation and that one that was discussed yesterday of repeated games in the Axelrod sense, that you add points many times, so you're making tournaments. Can you add tournaments to the spatial sort of cell automata point of view?
A kind of, or at least an evolutionary approach has been done by, I don't remember all the authors, but yes, that was one, and I thought of Michael Döberli. They did one as well with stochastic strategies, and Lindgren and Nordahl, they did it with binary strategies of varying memory size. And I guess the basic result is that space is favorable, so it would speed up the simulations. And but there were, from my point of view, there weren't too many interesting results from these simulations because it was shown by Axelrod that cooperation can evolve in the mixed situations, which is much harder environment than the spatially structured situation.
If you put them together, then it will probably enhance it a little more.
Sorry? I didn't understand.
Like you in a sense, this tournament is doing sort of a lattice in time, so to speak. And now you have a lattice in time plus a lattice in space. So the question is that if cooperation evolves more rapidly, if you have time, memory, and space. Memory.
Yeah. Yeah. Okay. So the difficult part is sort of the establishment of cooperation in time, and if you add the space, then that's only beneficial.
One more question. Correct me if I'm wrong, but I think your collaborator Sabo showed in the context of the prisoner's dilemma that if one put, for instance, on every 10th cell, the cooperator kept it fixed so that it could not be updated, or so it would always cooperate all the time, then the level of cooperation would break down.
Right.
Is there anything similar in the Snowdrift game?
That's an interesting point. I think in the work of Sabo, they used repeated interactions. I think they had 3 strategies. They had cooperators, defectors, and tit for tat. So I'm not sure. Just
now I remember. Yes.
so I think just in this scenario that wouldn't be sufficient. But if you allow for repetitions, then might be interesting in the Snowdrift as well. But I don't know.
So I have difficulties somehow, I'm trying to learn, I have difficulties with being surprised about the fact whether or not space helps cooperators in the Snowdrift game or not, because in the prisoner's dilemma, there's a clear asymmetry between cooperators and defectors, and the way how we set it up, we chose situations where defectors would dominate cooperators, so without space you don't get any, you have no cooperators at all. So whenever you find cooperators with space, then it's clear that spatial effects help cooperators.
Yeah.
Now in the Snowdrift game, once you relax this prisoner's dilemma condition, it seems to me that you generate more or less any 2-player game. And therefore, if you consider general 2-player games that have the feature where A and B coexist, it is not surprising that in some circumstances space helps player A, and in some circumstances space helps player B. So I wonder if we should be surprised by the observation. Or maybe more precisely put, can you find Snowdrift games where space does help the cooperators? And so you do have in your diagrams that for certain cost-to-benefit ratios, space does help the cooperators, and for higher ones it doesn't.
The reason for the extinction of defectors is that although it is beneficial to adopt a strategy that's different from your opponent, it's still always better or preferable to be surrounded by cooperators. And for high benefits of cooperation, this can lead to the extinction of the defectors. That's the only region where space turns out to be beneficial, because of this mechanism that cooperators can push defectors out of the system. But other than that, there's...
What I mean is, if we take any 2-player game where there's a coexistence between A and B...
But they are all Snowdrift games.
They're not all Snowdrift games, that's right. They're not all Snowdrift games, right? Some of them are not Snowdrift games, or using all of them as Snowdrift games. So, but then it's not at all surprising that sometimes space will help A and sometimes space will help B because of symmetry arguments.
Yeah, but then you would more expect something like, let's say, a step function. You know, where you have compared to the well-mixed outcome, that sometimes you're slightly below and sometimes you're slightly above, and then you're again below. And I think that here that's a different mechanism. However, I agree that it's not obvious why space should decrease the amount of cooperation. But it's hard to derive kind of geometrical arguments, because you would have to look at the transition probabilities of different particular local spatial configurations, and then to derive the transition rates of the different configurations. That's a very difficult issue.
I have a question popped to my mind, and I have maybe the courage to ask. How about if the underlying game is three strategies? I would imagine something like this, like the spy versus spy, and then you have one more spy, which is a friend of the first spy, in a sense, and you're playing in two scales this Snowdrift game. I was thinking, I was sort of, it's coming to my mind, for instance, in this example you gave about cancer, that the cancer sends a signal to sort of make the immune system to sort of don't see it. Is that right? So imagine that you find a medicine that somehow plays the same game with the cancer. So it's be like a third strategy. What would be the outcome when you have, like, instead of 2x2 game, a 3x3 game plus space?
I couldn't just like I had to guess. However, I think it's an interesting point, especially if you have a combination of different games, because the payoffs for example, for a drug treatment, they would be different than
Hierarchy of
yeah.
games like this.
Any more questions? Then let's thank the speaker again.
Sorry, announcement time. Thanks our collaborators and our sponsors. No, I'm just kidding. The question, we are going to have a van going to Covey Floor at about 5 to 12. It's going to depart from the parking lot, the main parking lot here on the top, the one near the hall and the bank. So people who would like to go to Covey Floor, they get at 5 minutes to 12, and they depart at around that time. It's important to get to Covey Floor before the big lines assemble there. We resume at 1 p.m. with Professor Rita de Almeida, and again, I remind you all, we have the barbecue tonight, so you may acquire the tickets for the barbecue. It's a bargain, it's 12 reais from the students, and you can ask Sueli about that. So, okay, so that's all I have to say. Thank you.
I have a very stupid question about the...
There are no stupid questions.
I noticed the dendrites, they like grow, extend, and often break. Why do they break? I mean, why don't they turn around and they close line?
Yeah, that's a